All right, and we're going to begin with what is happening in that lava lamp we watched earlier this week. Here is our lava lamp. I'm going to do my best to draw it. There it is, nice and quick. Here's our lava lamp, and here's our lava in the bottom. Our lava is going through a process at the bottom that makes it create those bubbles that rise to the top and then fall back down. And we thought about why this is happening in class. We have the process that some of you identified as heating happening in the bottom of the lava lamp. There's a hot coil that warms up those lava bubbles that then float all the way up to the top. The lava bubbles rise to the top because they're less dense. They're less dense because the molecules are moving faster, making them have to spread out, and then the bubble has less molecules in it. They rise to the top, and at the top, they begin to cool because there's no hot coil in the top of the lava lamp. As they cool, they get more dense, which means they come closer together, and they fall back down to the bottom, where they'll begin their process again. The cool bubbles fall to the bottom, they heat with the coil at the bottom, and then they rise up to the top. The same process is happening in Earth's mantle. Let's take a closer look. Here's our Earth. Believe it or not, that is exactly what our Earth looks like. Thickness of the crust, thickness of the mantle, thickness of the core. So there's our mantle. Our mantle is the part with that magma and lava that's always moving around through the mesosphere and asthenosphere. Our crust is really thin. That's the part of Earth that we live on. And it sits right on the top of the mantle with our tectonic plates that some of you mentioned in class. The crust is made up of rocky parts, just like dirt and other big rocks, that then can melt and become part of the mantle. That is a process that happens near volcanoes and seams in the Earth's crust. Now, the crust is cold. We live on it, and it's not boiling hot magma rock, but the middle, the core of the Earth, is very, very, very hot. And we're going to talk about specifically how hot it is next week. The very hot part of the core works just like the coils in our lava lamp. It warms the lava, and the lava rises. As the lava rises, it goes up to the crust, and it hits the crust, and then moves across the crust, just like those bubbles in our lava lamp, and then it cools at the surface of the crust because there's nothing heating it. It's far away from the center of the core. So then the cooler lava, you see my yellow pen, it shows our cooler lava, starts to float back down. Again, lava cools as it moves along close to the crust of the Earth, and then the cooler lava, because it's more dense, floats back down closer to the center of the Earth. And there are yellow arrows showing that nice cool lava going down to the center of the Earth towards the core, where it's going to get heated up some more and then rise again. This process is happening all over the mantle. So I can draw it over here, happening some more. There's another magma cycle, and there's another magma cycle. These two are going in opposite directions. Those convection currents that are being created by this heating process as the lava cycles through the mantle. This is going to cause some movements in Earth's crust. Lava cycles through the mantle, causing movements in Earth's crust. And this is going to cause plates to move. Let's take a closer look. Here, we're going to imagine we have a fault line. Let's draw a non-continuous part of the crust. There we go. And we have two plates. Where two plates meet is called a fault line. Those plates are riding on top of that magma that's moving underneath it. So it's going to draw those plates closer together. They're going to converge. That's right. These two plates are converging as they ride on top of that magma. as those plates converge, some of that lower plate is going to get heated up a lot, and maybe even that hard rock part of the crust is going to melt a little bit and be converted into lava and get integrated into the magma cycle. Now, don't worry, you're not going to be walking along someday and the surface of the earth is just going to disappear underneath you into some lava. The crust is 100 kilometers thick in most places, so we are not going to feel a lot of these changes, except in the case of something like earthquakes. When we feel earthquakes, it's a small but very dramatic shift in the Earth's crust. Now, let's take a look at what happens when we have an earthquake underwater. Here are two bits of Earth's crust meeting at a fault line. And those two pieces of crust can shift. They can do transverse, diverge, or converge shifting. I'm drawing transverse with these two arrows going in opposite directions. A transverse shift or a convergence of two pieces of crust can cause shock waves from an underwater earthquake. The shock waves on land create an on-land earthquake. Underwater, though, these waves translate into actual waves in the ocean. These waves will build up speed as they approach the shore and it gets more shallow, creating a tsunami. Which sounds like it should start with an S, but actually begins with a T. Now, one last part of all this movement, something you're all very familiar with, is the idea of a volcano. Let's take another look at the crust on our little Earth up here. Let's cause another fault line where two pieces of crust are coming together. Maybe not coming together, maybe they're diverging, coming apart. We have these two pieces of crust where they meet at this fault line. And let's draw, our magma cycle is going to be moving against each other, moving in opposite directions right now. There's our magma flowing through the earth, being heated by the core, rising up because it's less dense, and cooling at the crust. Then it floats down to the core where it's heated and then rises up again. At this fault line here that I've drawn, we've got a little gap as the two plates are pulling apart. Some of this magma is going to come all the way up to the surface of the crust, and as it emerges, it's going to be getting cooler. There's my cool color arrows. And as it cools, some of it's even going to harden into a rock. Some of it, though, is going to stay protected on the inside of other cooled and hardened magma that's now solid rock, like a volcano. And there we have a volcano. Very exciting. Oftentimes they don't erupt, and very rarely do they erupt looking like that explosive magma. But volcanoes are formed by the gaps in the plates. Not all gaps in all plates have volcanoes like this, but that is one popular example. So let's zoom out, look at this. Here are our volcanoes formed at our diverging plates. There it is, diverge, come apart, divide. And then let's look up top. There we are, magma cycle with our converging plates. And down below, we drew some transverse plates causing shock waves
occur
and
in
a
the
tsunami.
Pacific Ocean and Indonesia Ocean, because the Pacific Rim, a part of plate tectonics that's very active, has a lot of active submarine earthquake zones. However, they can also occur in the Mediterranean Sea and the Caribbean Sea. Good thing we don't live near those coasts.
And thanks for watching. Don't forget to fill out your form in Google Classroom.